let's talk about exponential functions, like 2 to the x, let's say. Let's say we have something like 2 to the x equals 8. How can we solve for x? Well, when we're solving for x, we want to isolate the x on one side. And to do that, we have to get rid of this x in the exponent and bring it down somewhere. But how do we do this? Well, to do this, we have to get rid of the base somehow. And how do we get rid of the base in an exponential function? Well, that's where the logarithm comes in. Logarithm, often written as just log, is the inverse of exponents. I'll just write that here. Inverse of exponents. Exponents. And if you know what an inverse is, or inverse operations like plus and minus, well, you know that if we have 3 plus some number, let's say x, and we subtract that same number, we're just going to get 3. Because these are inverse operations, they undo each other. And logarithm is the inverse operation of exponents, so they're undoing each other. So let me give you an example here. So hypothetically, let's just say our logarithm function undoes the exponent. So log 2 to the x equals 8. So if we go off this example, the logarithm should cancel out the base and give us x equals, and whatever we do to the left, we must do to the right. So log 8. And we learn later on in this episode that this is actually not the case, but this is just an intuitive sense for what a logarithm does. It gets rid of the base and isolates x by itself. Okay, let's work on the logistics of logarithms because we kind of just introduced it as a hypothetical function. So now we're going to make logarithms seem more real. Okay, one thing you might have recognized about exponential functions is that they're not all the same. So we can have something like 2 to the x, but there's also something like 3 to the x, and 4 to the x, and 5 to the x, and so on and so on and so on. This base is not always the same. So should that mean that logarithms don't work the same on all exponential functions? Well, let's just test this out. So let's say we have 2 to the x equals 3 to the x. Oops, not 3x, 3 to the x. And now what we have from logarithm so far is that it undoes the exponents. So if we take the logarithm of both sides, logarithm, this side, what we know so far is that it just cancels out the base. So we get x equals the log and the 3 on the base cancel. So we get x equals x. And if you remember that if you have an equation that is x in the x, we can reduce this to 1 equals 1 by dividing both sides by x. And if we have something in the form some number equals another number, then this means it is true for all values of x. But this is clearly not true. If we have 2 to the x equals 3 to the x, that is clearly not true for all values of x. They are different functions. So what's going on here? So it seems like our conjecture is correct, that the logarithms don't work the same for all of the functions. So how do we make the logarithms work with all of the functions? So this is how we do it. So basically, for logarithms, we have bases as well. So we can have log base 2, and this undoes 2 to the x. We can have log base 3, and this will undo 3 to the x. Or it cancels out the base, is how I like to think of it. And now this makes much more sense because they don't apply to all of the functions equally. Okay. Now, that we've got the properties of logarithms, let's introduce it. So a logarithm is the inverse of exponents. And how it works basically is if you have something like log base 4 of 16 equals 2. This is saying that 4 to the what number is 16 will be equal to the answer to our equation. And you'll see in the next step how this works. Again, if it's something like log base 3 of 9 equals 2, this is stating 3 to the what number will be equal to 9, and that number is going to be the answer to our logarithm. Now, if we look at other inverse exponents like 3 plus 7, we can write this in terms of its inverse, or subtraction. 3 plus 7 is 3 minus negative 7. So we just turned addition into its inverse, subtraction. And we can do the same thing for multiplication, like 3 times 7. That can be 3 divided by 1 over 7. We just turn multiplication into division. And similarly, we can turn logarithms, I'm just going to write base x now, logarithms into exponentials. And how do we do this? I'm going to start with actually an exponential function at first. 3 squared equals 9. Now, if we take the logarithm of 3 on both sides, log base 3, this log 3 and 3 cancel, and we get that 2 is equal to log base 3 of 9. And these expressions are equivalent because we just did simple algebra to bring this equation to this equation. So we just wrote an exponential as in terms of a logarithm. And let's see how this logarithm is working. So this is saying 2 equals log base 3 of 9. And basically, what a logarithm means, I haven't gone over this yet, but a logarithm is basically saying, if you have this base here, which is this base over here, if we raise it to the second power, which is this over here, that's going to be equal to 9. So let me start off as a logarithm. So like log base 4 of 16 equals 2. And basically what this is saying, if we look here, it's saying that 3 squared equals 9. So if we look at the same pattern here, this is saying 4, or our base, right? If we raise this to the second power, like this 2 is in this second power, that's going to be equal to this number here, 16. And this makes sense, right? We're just pattern matching, basically. We're seeing that this 3 corresponds to this base, and this 2 corresponds to this exponent, and this 9 corresponds to this value. And this basically pattern matching is how we can make logarithmic statements and exponential statements equal to each other. I do one more example here because I don't know if I'm quite explaining it clearly. So if we have something like, let's say 3 to the x equals 9, we can take the log base 3 on both sides, log base 3, and this will cancel, so we just get x is equal to log base 3 of 9. And here's our pattern matching again. Our base 3 corresponds to the base of the exponent, like on both of these examples. Our 9 corresponds to what the exponential is equal to, also like on both of these examples. and our x is the exponent. Also, like on these examples here, the exponent is what the logarithm is equal to. And this makes sense, right? Because in the beginning, we introduced our logarithm as the base being raised to what power is equal to 9. So the base raised to what power is equal to 9 will be the answer to our logarithm. And if you look here and here, these are the same statement. So hopefully that makes sense and it wasn't too confusing. We're going to end off this introduction by looking at how to evaluate logarithms. So let's have log base 3 of 9. What will this be equal to? Well, if you remember from the beginning, we introduced our logarithm as being 3 to the what power will be equal to 9. And this is 2. Another way we can think about it is our pattern matching from before. This logarithm statement, we can convert it into exponential function. So the base will become the base, the 2 will become the exponent, and the 9 will become what it is equal to. So this makes sense because 3 squared equals 9. But let's say we didn't know that this was 2, which we didn't know in the beginning, and just x. Well, we can verify that 3 to the second power is equal to 9. So our answer to this logarithm is 2. Okay, let me evaluate one more logarithm. Log base 4 of 16. Well, this is asking again, 4 to the what power is equal to 16? And that's 2. Another way we can think of this is converting into exponential form, where 4 is the base, and 16 is the thing that it's equal to. And we're looking for the exponent here. And that is the answer to our logarithm. The exponent is the answer to our logarithm. And we can see here that 4 squared equals 16. So 2 is the answer to our logarithm. Now, this video was a little advanced compared to my other videos. So if you have any questions, please ask them in the comments below.